Today, we're going to talk about statically indeterminate systems. To do this, let us consider a simple rod system as illustrated here with a built-in end at A and a free end at B. Apply some known loads to that. At the mid-span, we will apply an axial load P1 and an axial load P2 at the end at point B. Now, if we want to analyze this system using the principle of solid mechanics, the first step is always the free body diagram. So we remove the built-in condition at A and replace it with the appropriate reaction forces. In this case, a horizontal reaction at A. If we then look at our second step, it is to look at equilibrium. And if we take some of the forces in the horizontal direction, we see that our reaction at A is equal to the sum of P1 and P2. We thus can say that this problem is statically determinate because we can solve for all of the reaction forces using the principles of statics alone, just using equilibrium. What if there were more unknowns though? What if we replaced our known force P2 with an unknown reaction RB? Our equilibrium then would result in one equation and two unknowns, and we would not be able to solve the problem using statics alone. Thus, the problem would be called statically indeterminate. We need something in addition to statics in order to solve that. So that's the main difference between statically determinate and indeterminate. But when can these differences physically occur? If we look at our two free body diagrams, they're very similar except for which forces are known and unknown. If we take our left free body diagram and recall what it was in reality, this reaction represented some sort of boundary condition that held the beam or the rod in place. If we look on our right then, it should reduce down to a rod that is fixed at both ends. There is a constraint at both ends that creates an unknown force. In this case, the problem is over-constrained. There is too many things restricting the deformation of it, and it is that restriction that generates the unknown forces. So we need to be able to formulate how deformation occurs in this problem. If we examine the deformation constraints in our problem, we can see very clearly that the overall length of the rod cannot change. It is fixed between two walls. So our compatibility equation is delta AB has to be equal to 0. Now we already determined a force displacement relationship for axial loaded members, and that is delta is PL over EA. However, this was only applicable if the force was constant along the entire length of the rod. And in our case, that is definitely not true. If we look at what is occurring along the length of that rod, and we do a free body diagram between A and C, we can see from our free body diagram that our internal force has to be equal to RA. Similarly, for CB, our internal force has to be equal to RB. And we get an axial load diagram looking like this, varying from RA along length AC down to RB along length CB. Thus, we can break up the problem into two axial loaded members in series and decompose the compatibility equation into two elongations, delta AC and delta CB, and they have to sum to equal 0. We can then formulate two force displacement relationships for length AC and length CB as shown here. With these additional equations, can we actually solve? Well, we started off with our equilibrium equation, which was one equation with the two unknowns, RB and RA. We came up with a compatibility equation that actually introduced two additional unknowns, delta AC and delta CB. So now we have four unknowns and two equations. But then we also have two additional force displacement relationships, and they don't introduce any new unknowns. So we get four unknowns, four equations. We can solve for the unknown reaction forces. And that's effectively what we need to do in a statically indeterminate problem. Look at how the stiffness and the geometry, the area, lengths influence the deformation, and that will determine what the unknown reaction forces are, those redundant reaction forces. Now, if you look at the overall procedure we took, it was using the same principles we've talked about for solid mechanics. First, establishing a free body diagram with your sign conventions, the directions of your unknown forces, and that will relate to the directions of the deformations. The second step is always equilibrium of forces and moments, and this is where you find out if your problem is statically determinate, if you can solve for all your unknown forces and moments, or if it's statically indeterminate. You then have displacement compatibility and force displacement relationships to give you those additional equations you need in order to solve a problem. And once you have the same number of equations as unknowns, you can solve for your unknown forces. And then the last step is always to answer the question. Seems trivial, however, sometimes a question asks you about stresses and deformations, and we get caught up in first determining our unknown reactions that we forget to actually calculate what we really want to know.